In this segment, we'll look at how renewable natural gas can be generated from biogas and landfill gas. We'll also look at other alternative fuels near the end of this video. So renewable natural gas, unlike electricity, is putting landfill gas and biogas directly onto the natural gas grid where it's going to compete with fossil natural gas. So it can be a more efficient way of achieving greenhouse gas reductions than putting electricity generated from landfill gas or biogas onto the electrical grid in jurisdictions where the electrical grid is already pretty clean, which is the case in Ontario, Quebec, BC, and other places. To be able to put natural gas into our normal appliances that burn normal fossil natural gas, the biogas or landfill gas has to be purified to a very high standard. So everything we talked about for the other technologies, moisture, particulates, sulfides, and siloxanes, all needs to be removed. We also need to get rid of the carbon dioxide. So this is a huge portion, half or 40% or so of our biogas or landfill gas. Any nitrogen or oxygen which has entered the system, and that's very common in landfill gas, as well as any non-methane organic compounds that happen to be in that gas. So the natural gas in the grid system is about 96 to 98% methane. So we need to get our biogas or landfill gas that might be about, 40 or 50 or 60% methane all the way up to that 96 to 98%. In the picture on the right, you can see a natural gas, a biogas or landfill gas upgrading system. And you can see there's a lot of pieces to it. All those are necessary to get that high degree of purification. And we'll walk through what each of those is doing in this segment. Renewable natural gas has a huge potential for offsetting some of our existing natural gas usage. In Canada, as shown in these figures here, this is from a 2014 report, just 10% of the total potential to produce RNG could power 1 million homes in Canada, or take the equivalent of 1.8 million cars off the road in emissions savings. So there's a lot of benefit to be gained by developing our renewable natural gas resources. All this methane would just be being flared and wasted anyway. So RNG technologies allow us to essentially have those flares located in everyone's furnace or natural gas vehicle where it's actually being used rather than just wasted and the heat just flowing off into the atmosphere. Now we've seen the figure on the left before. This is our gas quality that we expect from biogas and landfill gas. On the right is a pipeline quality natural gas specification. So you can look down it and see all the different parameters that need to be controlled to be able to put our gas onto the grid where it can be safely used in the existing pipes and existing natural gas appliances. So this is the reason why we need to do all this very careful purification, is to meet this pipeline specification. And it's going to be a little bit different for different utilities, but generally very similar of getting it very high purity of methane with not too much other components in the gas. So the largest component we need to remove is the carbon dioxide. So methane and carbon dioxide are the two major components of the biogas or landfill gas. Fortunately, the actual molecules of methane and carbon dioxide have some important differences that allow different separation technologies to be applied to getting them in two different places and sending the methane into our pipeline and the carbon dioxide off in our tail gas stream. So methane is a larger molecule and is also very very sparingly soluble in water. Carbon dioxide, on the other hand, has much better solubility. It has this polar covalent bonding because the oxygens are pulling electrons so hard. That improves its solubility, and it also gives it the molecule kind of different interactions with different materials. And it also happens to be a smaller molecule. So these differences can be exploited in a number of technologies that separate carbon dioxide and methane. So the first one we'll talk about is membrane separation. So this is just a very, 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 very small filter that's working at the molecular level. So because the methane molecules are so small, they're able to pass through a filter where carbon dioxide molecules will be retained on the other side. And this is typically accomplished with a hollow fiber membrane filter, which is shown on the right. So these are like little tiny straws with very, 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 very small holes in them. And the reason we want to have very many small fibers is to increase the surface area. The more surface area, the less pressure will need to be applied to push that gas through these really, really small holes. So you might have thousands of fibers in a module, and then you might have a few modules just to be able to treat the amount of gas that you want to treat in your system. Another system that does the same thing as the membrane is a pressure swing adsorption system. So it operates on the different sizes and polarities of the molecules again, but instead of forcing them through a membrane, it pressurizes them against an adsorbent. And because methane is nonpolar and small, it is able to permeate into the adsorbent and kind of stick there, where carbon dioxide will not be able to permeate it. And so you'll have all this methane building up in the absorbent and the carbon dioxide flowing past it. And then that same system can be depressurized to push all the methane back out of the adsorbent and then switched back over. So you need a few different modules because you run it in batches, but you're essentially soaking up all the methane, blowing everything else past, and then squeezing out all the methane from that absorbent and putting it into your gas stream that you want. Two other systems, so again, these are doing the same thing as the membrane and the pressure swing adsorption, just in a different way, are water wash and amine scrubbing systems, and they operate on similar principles. So both of them exploit the solubility of carbon dioxide and the relative insolubility of methane. So in these systems, they'll use packing medium to get a lot of surface area between water or amine solvent and the gas. The carbon dioxide is going to become trapped in that solvent at a higher rate than the methane, which is not that soluble. So the methane just flows right through it. And then that solvent or water can be depressurized to flash off the carbon dioxide that has been contained in it and then sent back to absorb more carbon dioxide in another unit. So similar to the pressure swing adsorption, you need two systems operating at different pressures to be able to sorb and desorb the carbon dioxide. It just happens in the liquid phase instead of the solid phase. So that's to remove our carbon dioxide, which is our largest portion. For nitrogen and oxygen, so typically you'll only need to worry about this in landfill gas. If your digester is leaky somewhere, you'll get a little bit in, but much bigger issue for landfill gas. So pressure swing adsorption automatically will take care of a little bit of nitrogen and oxygen just by the same principle. It's not going to be adsorbed the way the methane will. If you have higher nitrogen and oxygen, you might want to add an additional pressure swing adsorption unit to clean more of this out after your initial one. Another approach to removing oxygen in particular is catalytic deoxygenation. And you're literally just burning the oxygen that's in the gas with some of your methane. So you don't want to do too much of this because then you'll lose your methane, but it's an easy way to polish off low levels of oxygen. And obviously you don't want to ignite your mixture. So this is happening over a catalyst, which lowers the energy required to actually burn that oxygen off, and it will end up as water and carbon dioxide in your mixture. Which is going to lower the flammability, and that happens over a precious metal catalyst. Now sulfides, we talked about a few techniques for getting sulfides out of our engines and micro turbines. A lot of our technologies, the water wash and amine scrubbers, PSA and membranes, they address sulfides to some degree, but in streams where there's heavier sulfides, you might also use some of those technologies. So in the water wash and the amine scrubber, sulfide is quite soluble. You'll be able to remove some of it in that solvent stream. In the PSA, again, it's not going to be retained where the methane is retained. It's going to flow through with the other gases, but only to a certain extent. And then again, with the membranes, the H2S should permeate the membranes with the CO2. But if you have too much hydrogen sulfide in any of these systems, it's going to end up with our methane molecules. So in those cases, you'll want to have more hydrogen sulfide removal on the front side.